this question. So the signal looks like this, something like that. Okay, it doesn't really matter, right? I drew it terribly. Okay, Rana, are you there? Are you guys still hearing me?
Yes, I'm here.
Okay, I just want to make sure you guys are hearing me loud and clear. Okay?
Yes, everything is good.
Okay, so the thing that you have to work with this is this. Is I tell you, okay, well, this voltage, right, as defined in this plot, right, goes from -4 to +4. Okay, and then obviously this is a composite signal, right, and the frequency ranges, right, from a spectrum perspective, right, goes from 125, right, to 250. Okay, and then my question is this, right, is that I require, right, a quantizing signal to noise ratio, right, of greater than 31.75 dB. Right, so those are the requirements given to you. Oops. Okay, and the question is, what is the required or the resultant bit rate for you to do a PCM on this into the bit stream? Well, we said there was 3 things, right? You need to figure out, number 1, right, what sampling is. Number 2, the number MB, and then number 3, right, the data rate. Right? It's that methodical way of sort of solving through this particular problem. Okay, so if I start up and I say, okay, I want to do sampling, how do I do that with sampling? What is the rule to do sampling?
2 times F max.
2 times F max. Okay, so F of S, right, must be 2 times F max, which is this value here. This is F max. Okay, not 2 times of bandwidth, right? Did anybody do 2 times of bandwidth? Okay, good. Okay, because that's a very common mistake, right? So then what it really is that then F has to be at 500 hertz, right? Samples per second. You can write either hertz, right? So units matter, right? So hertz or samples per second. Now, the next thing then is this, okay? I need to solve for the number of bits required. And I know that, right, when I do encoding, right, in terms of that, right, I need to say SNRQ, right, which is 6 MB minus 1.25. Okay. Should it be greater than or less than? Because Chantal says, right, it goes up or down. You don't have to memorize that, right? The question is this: should it be greater than or less than? Should it be greater than or less than? Because it says this, right? You want a quantizing signal to noise ratio of above 31.75, which means, right, when you rewrite this, is that this thing is 31.75, right? And you need to be above that. Right? The number of bits you assign must be greater than 31.75. Does that make sense, Chantal? It's not about memorizing it. You're using the equation, right, which was given to you as an inequality, and you say, okay, the end result of this in dB must be greater, right, than 31.75. So then if you solve for this, if I go on to the next screen, right, then your NB must be greater than 5.5. This greater than is sufficient to tell you then NB, oops, not 6 MB, but MB. Oops, I cannot erase this, but I can cross this out. Must then obviously take the ceiling of this, which is 6 bits. Remember, right, I said this, MB must be an element of integer. That is very important. Right? L must be a power 2 value. So if you have this, then the only thing then you have to say, okay, well, what's the data rate? Well, the data rate is actually F of S times N of B, right? Which is 500 times 6, right, which gives you 3 kilobits per second. Does everybody follow?
Yes.
Okay. So again, you should come to any problem that you see now, right? You should be able to have the ability to say, okay, this is the problem. What is it asking for? And if I know what it's asking for, what are the information that I need? Okay. And I want you guys to go on a path of what is known as deliberate practice. So, right? So I don't want you to be just doing problems for the sake of doing problems. I want you to do the problems, right, deliberately, right, to get better and gaining the knowledge behind each problem. Right? And there's a difference to it, right? Mechanically solving a problem, right, versus actually working through a problem to a solution. Right? It is very important, and that's what deliberate practice is. And this is where you will see is find that if you actually work on the practice problems, it's actually very helpful. Okay, but I believe the equations, right, in anything that is obviously necessary is given to you. Right. Obviously, I don't tell you what FS is because that's really right something that you should know by now. The FS is always 2 times the highest frequency component. Okay. So I want you guys to it's important to realize that, right, is that now you're in the middle of the course, right? You should have, if possible, right, try to be able to link things across different modules. Right? Because real world problems don't just question you on one single specific topic. Right. And you should not be relying on formulas. You should be working based on, okay, these are guidelines, right? And as I said, right, I'll give you sort of the formulas as you work through, because I don't expect you to memorize them, right? Given that it's actually a closed book quiz, right? I'll give that to you. But you need to know how to use it, and knowing how to use it is actually the more critical thing, right? As you get onto the jobs, right, and you're working, right, formulas you can actually easily look up. But knowing how to use it, right, and use it correctly, obviously, right, is the difference between sort of you and everybody else. Okay. Okay, so I want you guys, right, as you know, the quizzes will get a lot more and more in-depth as we proceed on, right? Only because, and in-depth, what I mean by in-depth is not that it's a more difficult quiz, but it's starting to tie all the different pieces together. Okay, well, we have taken an approach, right, that goes chapter by chapter, right? At the end of the day, right, to solve a problem, right, you require the knowledge that you've accrued, right, over time. Okay, and that's where your value add is. Right. So yeah, exactly. Right. So really, right, the quizzes are trying to tie things together, and I want you to start thinking that way. Okay. Too often than not, right, you only study for the problem, and that's not the right approach to study. Right. You should be able to aggregate the information collectively, right? Use them, right, in a way, because that's where your value is. If all your answers are simply, right, a result that you can simply Google or use any search engine for, okay, you haven't really learned much, because you haven't presented much value, right, as an employee to a company, right? Because then you really need somebody who can use the search engine, right? Your value add to any company, right, is whereby you can now tie the pieces together, right? Which obviously at this point in time, right, search engines are not very successful at. Is that clear? Everybody, right? So again, right? Don't get too sort of taken back by one quiz that you didn't perform as well, right? The idea is that you understand where your sort of point of fault is at this point in time, right? And you're working towards to sort of getting better at it. Okay, everyone.
Yes.
Okay, and it's a really important thing to try to master over time. You don't get it overnight. Okay, it takes time to sort of master that. Okay, oops. Let's get onto this mode here. Okay. Okay, so let's start it with sort of analog transmission, right? And then the goal is that if we can get started with this, then you guys can work on sort of the assignment 2 in completion by the end of Wednesday next week.
question before we carry on.
Yeah, go ahead. Yeah.
The remaining questions of assignment 2. How difficult are they? How challenging are they? So should the given time be sufficient for us to complete them, or
Can we make? Yeah. So the first question is not a simple question.
Okay.
I'll tell you that. The third question is a very simple question.
Okay.
Okay. So let me get through the material first, Rana, and then can you raise the question at the end of the class? If I can give you sufficient insights to how to solve the problems, right, then you should be on your way to being able to solve it. Okay. If you feel that you haven't gotten the insights, then obviously, right, we can consider, what happens to the assignment. Okay. But let's go through. Let's take the time to go through. We have more than 2 hours to actually try to do that.
Okay. Perfect.
But I'll tell you that is that what I'm hoping that you guys are doing, you're focusing more on the learning process, understanding and gaining insights, than trying to just do a problem. Okay. Question 1, sorry, is actually a very, once you understand, it's actually very, well, at least that's what students have been telling me in the past, right? It's very enlightening in terms of how data rate is being. Remember, right? The question I want you to answer is not about memorizing formulas. The question I want you to answer is not about applying the formulas. But the high-level question of why you're really doing this course is, how do you increase data rate in a system? Right? And to understand that question, to respond to that question, you really need to get insights on how, in the first place, what are the factors that determines data rate, before you can even make an approach to say, okay, of all of these parameters that I can tune, which is the one that is most effective under this scenario to be able to increase the data rate, and obviously correspondingly reduce the latency. Is that clear?
Yes.
Okay, so is that insight that I want you to get. It's not about formulas. It's not about just superficially understanding the material, right? You're in post-secondary education, right? You need to get to the depths of understanding. That ability to see the problem, understand the problem, right, and piece things together on your own is an extremely valuable skill set. Okay, so let's just go through with that, and then Rana, please raise that in the last 10 minutes of the class. Okay.
Will do. Yeah.
Okay, so I want to get on with analog transmission. As I said, right, this is a slightly more difficult section, and it is also the very last module that will deal with anything that has got to do with sine and cosine, right? Until such point, maybe if you will see a final exam or something like that. Okay, the idea is this: is analog transmission, as I said, is not going to go away, right? Just like digital transmission is not going away. Okay, in fact, analog transmission will become more and more prevalent. I just gave you, right, the motivation. If I were to say that all that you have to do on a mobile device is that you have to connect it physically with a cable, like a USB cable, will it change your usage model of the device? And in most cases, the answer is yes, true. Right? If you're forced, right, to use all of your mobile devices with the need to have a cable attached to it, right away it changes the convenience, right, and the usability of the product. Would you agree so?
Yes.
Okay, and part of the reason why all of these consumer products have proliferated, right, in the last little while is because of the ease of convenience. I can hold a laptop. I can, in fact, most users don't use laptops anymore. Many of you are transitioning into sort of the hybrids of laptops, tablets, and so on and so forth, because really all you need is a screen, right? And everything else follows along with as such. Okay, so for that reason, okay, analog transmission is not going to go away, right? Because anytime we deal with Wi-Fi, we deal with cellular and other sort of wireless technology, including the likes of Bluetooth, NFC, all of which all of you use almost on a daily basis. True? I mean,
Yes.
you must be on Wi-Fi. You must be on cellular. In fact, in most developed countries, some users have multiple cellular devices. You must be on some kind of form of Bluetooth. Isn't that true? Okay. And in most cases, who actually uses tap to pay, like sort of tapping your banking cards, right? Visas, credit cards, debit cards, right? To pay. In fact, that is actually the preferred method of payment now because we're moving towards a cashless society. right? Pandemic or not. True? Okay, and all of that obviously, right, is some kind of radio waves being transmitted. Okay, so I can pretty much sort of assure you that probably in your lifetime, certainly in mine, right, analog transmission is not going to go away. Okay, so the question is this, right? Okay, it makes sense that, okay, if I have something in digital, that I need to obviously convert to analog for transmission. True?
Okay.
What about if something is really analog? Just like when something previously was digital, I had to also do line coding to get it to a digital signal. So what am I doing here in analog? Why is it that my human voice, which is analog, right, which is the analog data, needs to be converted to another analog signal for transmission? Why? So the first case is very, very, very simple. There's tons of digital information. Anything coming out from your tablets is going through a D2A if you're on the Wi-Fi network. Right, everything coming out right through to your network adapter is actually in digital, and then obviously you're transmitting that over a wireless, right, Wi-Fi signal, right, if you're on Wi-Fi. So the question very simply is this: digital to analog makes a lot of sense. Why is it that we have to do analog to analog? Can anyone motivate that? Data to signal, but why? It's already an analog signal, right? The analog data that I have effectively could be transmitted without conversion to analog. Sure, okay. But the analog signal, even if I convert to an analog signal, can also suffer attenuation. True? Not a hearing aid, no. Okay, so keep that thought in your mind, okay? Because obviously it is very important that you understand why you're studying something before you actually, right, go through the details of it. Okay, so let's start with D2A because it's the most obvious thing. And in fact, D2A we've seen quite a bit. Okay, so the idea is this: is that I have some information that's really digital, right? This happens all the time on your laptop systems that you might have, right? On your tablet systems, where a lot of the data is actually generated, right, in sort of a logical state, right, in the devices that you're actually using. But what I want to do, right, is that I'm going to now transmit an analog signal, right, which in your use case, right, would be either Bluetooth, NFC, or Wi-Fi or cellular, right? 4 different use cases, right, to attain that. At the end of the day, right, then I'm going to use this analog signal at the receiver to retrieve the digital data, right, that this analog signal was intended to carry. So how do you think we do this? You actually have been exposed to this. How and what mechanisms do we have to do a D2A? Does everybody remember? Think of a sine wave. What parameters within a sine wave do you have to use it as a means of representation of the actual data?
Frequency can be used, amplitude can be used, and phase.
That's right. And
Phase.
exactly. Or, yeah, right? Or a combination of these parameters. Does everybody see that? We can change amplitude, right? We talked about it. Shanghai, if I'm going to transmit to you 1010, I can tell you that obviously if I transmit to you 1010, amplitude of 5 and 0. I can use different frequencies. We've seen that. And then obviously I can use phase, right? Which is obviously your time shift with respect to time equals to 0, right? But I'm going to go to another technique where actually, in fact, right, that I can change and encode using a combination of this. In fact, I could change both amplitude and phase at the same time. Why not? Because it gives me more degrees of freedom. In fact, the reason why, right, 802.11ac or your LTE systems, right, can attain the high data rates is because it's actually using a combination of the sine wave, which is in fact what we call a QAM scheme, quadrature amplitude modulation, that changes both amplitude and phase. So let's take a look at all of them. Some of it which is straight up review for most of you. Okay. So the idea is this: I have some digital data. I need to change some parameters of this analog signal, which in our representation is that of a sine wave. Right? And we know within the sine wave, right, there are 4 parameters really, right? A, F, P, and then obviously there's wavelength, but we don't deal with wavelength in this particular course. Okay, so what then I do is I change A, I change F, and then I change P, or a combination. And then I get some kind of a signal representation, right, for digital transmission. Okay, so remember, right, how we transmit, right, in its most base fundamental form, right, is the use of something known as a sine wave, right? And previously we have motivated and said this, right? A sine wave is nothing, right, defined by its peak amplitude, which is A, its frequency, which is F, and obviously its phase, P, right? We use the Greek symbol theta, right, to represent that. In a time domain plot, right, this has peak amplitude of 5 volts, right, because this peak amplitude is 5. There are 6 peaks here, so it's frequency of 6, and a time shift or a phase of 0 because it starts at 0 for a sine wave. Okay, so if I say this, okay, if I have a high amplitude, this could be a logical 1. Shankai receives this, right? Or a low amplitude, this is logical 0. Shankai receives these, so he has 1 0 1 0 1 0 1 0. Right? So to give an example, right, of what we're driving at, right, which is what question 1 of the assignment really is trying to get to, right, is this: is that you can get this, right, as a high amplitude, right, and this is a logical 1, right, and then a low amplitude, right, of a logical 0. So if you want to set the bit streams, right, 1 0 1 0, then you'll be drawing something like this, right, and something like this. Does everybody follow? Okay, we'll get more to that, but that's what we're trying to do. Okay, we're trying to find ways of representing highs and lows. What is the issue with using different amplitudes? In fact, what is the issue with strictly using amplitudes? Anyone? Is there any sort of impairments if we use amplitudes? Not stable. We have a term for that. It starts with an A. What do we call that? Power. And what happens to the power on transmission?
Attenuation.
Attenuation, exactly. Which means that there is a possibility, right, a probability, right, that this high amplitude, by the time it reaches Shankai, right, has dropped to this level, and he correctly decodes an incorrect bit. True? Right? He did it correctly based on the standards. Okay, if you receive at this amplitude, so he did it correctly, but because of attenuation, he actually decoded the incorrect bit. So then we say, okay, maybe amplitude is not the best to do. Perhaps what I could do is I could use different frequencies. Right? So 6 oscillations versus 12 oscillations. What is the issue with using frequency? Does anybody remember?
Noise?
No, it's not noise, because remember, right? Even if the amplitude goes to 0, we can still decode it. But what is the issue with using frequencies? Has anybody heard about the auction of the 5G bands? Anybody heard about the auction? That was just on the news that the federal government has decided to delay the auctioning of the 5G bands. Oops. Yes. What about it, Zikang?
They have to be purchased and they are expensive.
Exactly.
Frequencies.
Exactly. So remember, right? If I want to transmit 1 bit, right, I need 2 frequencies. If I want to transmit 2 bits at a time, I need to have 4 frequencies. If I want to transmit at 10 bits at a time, I need 1,024 frequencies. And they're not cheap, right? The auctioning of all of these spectrums, right, run in the billions of dollars. Not hundreds of dollars, not thousands of dollars, but billions of dollars. Okay, just so that you're aware. Okay, keep those in mind, okay? But the nice thing, obviously, with frequencies is that, right, the amplitude attenuation impairs both, right, frequencies. So which means as long as they don't go to 0, it is potentially possible for you to still retrieve them. Okay. What about phase? So this, I could say this, right, Shankai? If you receive 0 phase versus 180 phase, this is a 0 and this is a 1. Right? So amplitude doesn't matter, frequency doesn't matter. What is the issue with this, Shankai? Why not just use phase all the time? Anyone other than Shankai?
It might cause delay.
What's that?
It might cause delay because of different phases.
Yeah, it might cause yes. So if I refine your sort of solution a little bit, right? What happens is that right? You need to know where time equals to 0 is before you can even. It's not about causing the delay, but it's really about I'm transmitting at this phase, but the receiver needs to know what your reference to time equals to 0 is. Right. Otherwise, you won't know what the phase is. Like I can receive something, and you're right. There might be delays to which phase shifted it. But before I even know that it was phase shifted, I need to know what your reference to time equals to 0 is to even detect that there's actually a phase shift. Right. And that's the more difficult problem. Okay. It is true, right? Obviously, right. There might be delays which resulted in more phase shifts. I think that's what you're trying to say. But the more important thing is that I actually need to know what time equals to 0 at the sender because I'm just a receiver. Remember, I'm receiving this signal blind. A signal's coming to me, right? And I need to figure out what time equals to 0 is. Okay? So all of these, right, that we've been exposed to, right? If you go back to sort of 2 modules, right, in the introduction to analog signals, we talk about all of these. Okay? Today, what we're going to do is that we're going to use this, right, to further look at how, in fact, analog transmission is being achieved, right, through the use of amplitudes, frequency, and phases. Okay, but first, right, I want to sort of bring an analogy back to the digital transmission. Okay, the same thing exists, right? If everybody looks at this equation here, there is still the N, which is the data rate. There is still the S, which is the signaling rate, right? And there's still the R. But now R is still, instead of log 2 of L, right, in terms of R as in NB, R is now, right, the number of data elements in one signal element. Okay, I want you to be aware of terminology here. Okay, the data elements are still the bits. The signal elements is now used interchangeably with the term called symbols. Let me write down this for you. Okay, so the book calls it, right, signal element. Right, this is equal to the use in most literature, right, called symbols. Okay, and the number of different signal elements, right, is L, which means the number of different symbols is also L. Okay, so it has the same analogy to digital, right? It's just that now we use L, right, to represent the number of different symbols. So that's really the same. The big change really is that in most cases, analog is never transmitted baseband, but analog is transmitted using, right, a higher frequency signal called the carrier frequency. Remember, right? And this forms the the basis of question 3. Okay, is that if I have a baseband signal, right, and let's assume that this is human voice, 0 to 4K, right, and another human voice, 0 to 4K. If I transmit both at the same time, what happens? It will be like 2 individuals talking at the same time. I'm talking and Rana's talking at the same time. What happens to the signal?
It got overlapped, and then you can identify who is talking.
Exactly, right? So there is going to be interference, right? The simple term is actually called interference. Okay, what do we do to radio stations? what do we do to radio stations?
Tuning into a certain frequency.
Exactly. We use something known as the, remember right here, I'm calling right, the carrier frequency here, okay, is in fact, I now bring the first radio station, right, to a carrier frequency of 94.5 megahertz. And I bring the second radio station, right, to the center frequency of 95.3 megahertz. Does everybody see that? Yeah, this is the notion of carrier. Why? Because if I were to transmit them purely in baseband, these two signals will overlap in frequency and interfere with each other. But I could use the technique of modulation, right? And I can bring this up to a higher frequency at 94.5, right? Having a 0.8 megahertz bandwidth, and bring this up to 95.3, still having a 0.8 megahertz bandwidth. Okay, so the interesting thing is the reason why we can have so many channels going on, right, is really something known as channelization, right, or frequency division multiplexing that we'll see also a little later today. Okay, so all we did, right, is we use a higher frequency signal, right, what we call the carrier, right, to carry the information. And this allows us, right, to move away from baseband and have simultaneous transmissions, right, of different streams of information at the same time. Right? An example of which, right, would be this, right? If I say this, okay, Shankai and Rana wants to speak at the same time, true? Which they did a few moments ago. Okay, but I could say this, okay, Shankai, I want you to speak at baseband between 0 and 4K, but Rana, I want you to raise your tone a little bit, and I want you to speak everything between 4 and 8K. If I'm able to tune to those two channels separately, then in fact there is no interference. Is that clear in terms of what the analogy is?
Yes.
Okay, so let's do a straight out problem on this, which is really, really fundamental, right? So we know that the relationship is still R, right? If you go back to this, right, it's still R equals N over S. There's nothing, it's not any different, right? R is still N over S. Okay, so if I tell you this, right, a signal, right, and in this case it's analog, carries 4 bits per signal element, and there are 1,000 of these signal elements per second. What is the bit rate? What am I looking for in this particular problem? Am I looking for R, N, or S?
R.
No, I want to determine the bit rate. Is bit rate R, N, or S? N, exactly. So how do you solve for N in this case? So the question now is this, which is R and which is S?
R is the 4 bits per signal.
Exactly, right? Because it's 4 data elements per signal.
Per signal, right? Yes.
Exactly.
And S is the number of signals, so 1,000, sorry, signals.
Exactly. So what's the bit rate then? If there's 1,000 of these signal elements per second, and each of these signal elements carry 4 bits, what do you expect the bit rate to be?
1,000 times 4.
Exactly. Right? Straight out application, right, of R equals N over S. But the important thing, obviously, right, is why I show you this example is because I want you to be clear, right, which parameter is defining R, which parameter is defining S, which parameter is actually defining N. Right? The equation hasn't changed from sort of your digital case, right? R is to N over S. Okay, but you again need to be able to extract from the question, just like in previous questions, what R is, right? Based on obviously its definition. R is always the number of data elements per signal elements. 4 is R. Signal elements is the number of signal elements. So S is the signaling rate, which is obviously the number of signal elements per second, right? And of course, you're trying to determine bit rate, right, which is N. Okay, where N obviously in this case is R times S. Okay, is that clear?
Yes.
Okay, let's try another one. And I want you to do this on your own, right? Take a few minutes to do this. There's an analog signal and has a data rate of 8,000 bits per second. And I tell you now the signaling rate is 1,000 baud, right? Which means 1,000 signal elements per second. Can you determine the number of data elements that are carried by each signal element? What am I asking you to determine here? And then the next question is, how many different signal elements are required? On your own, I want you to do this because this could be very helpful for you in your next quiz. Okay, take a few minutes, right, and try to define. Again, this is a play on R equals N over S, right? So I'm asking you, right, to use R equals N over S to solve this problem. At the same time, determine the number of different signal elements that are required. Okay, on your own, take a few minutes. So the first question, right? Determine the number of data elements carried by each node. What is that determining?
R.
R, exactly. And what's the value of R? R equals to N over S, right? So you get, obviously, right, R equals N over S, right? That gives you 8. But how many different signal elements are needed? The number of different signal elements, right, is L. Right? Remember, right? If we go back to the definition, and L is the number of different signal elements. Right? L is 2 to the power of R. Right? And so therefore, right, 2 to the power of R, which is 2 to the power of 8, 256 different signal elements.
So signal elements is same as signal levels.
Exactly. Precisely. But because, right, we don't just have voltage levels, because we can represent them either in amplitude, frequency, or phase.
That's why they called them elements.
Exactly.
Okay.
Because they are just not purely like digital, which is just voltage levels. You see what I'm saying?
Yes.
In digital is very simple. There's only one dimension to which is voltage.
The voltage, yeah.
But in analog transmission, there could be a combination of or individual components of A, F, or P. And that's why they're called signal elements. And we represent them slightly different. We'll get to that in a few minutes, right? But nonetheless, you see that it is the exact same definition as in digital, but just represented slightly differently. Is that clear to everybody else, like, in addition to Rana? Is that clear? Okay, this is critical, right? Because this is the first step of how you actually determine bit rates, signaling rates, right? And obviously, right, your goal is to increase the maximum number of bit rates possible.
Sorry, could you repeat again?
Yeah. So remember, right, in signal elements that we have, right, we call them we call them signal levels.
Okay.
Right? The number of voltage levels that we can have. But in analog, we call them signal elements because the signal elements can be of different dimensions. It could take on the dimension of amplitude, phase, or frequency, or a combination of. And so instead of just calling them L is the number of levels, right? We call them really, right, the signal elements, right? The number of different signal elements. And we'll show you the different dimensions in a few seconds.
And that what confused me a bit, because I know it's 8 bits, just signal elements. I was wondering, is it the same as signal levels? So that makes sense.
Yeah, exactly. Because I'm not just in digital, there's only one dimension for me to change.
Yes, it's the same concept, different
It's the
shape
same.
or different, yeah.
Exactly. But in this case, right, in digital, we can only change the voltage. But in analog, we can change either the amplitude, phase, or frequency.
Yeah.
So instead of simply just calling signal levels, which is
It's an
a
element.
exactly, we call them a more generic term, right? They're elements because they can take off any, right, of these parameters. Is that clear to you, Zikang?
Okay. I just are you hinting that the element is just a mix of things, like mix of characteristic? That's it.
Yes.
Okay. I was a little bit confused about like is it like actually one single thing's there?
No, it could be single. It could be single or it could be a
Okay.
combination.
Okay, so
Oh,
it's like
it
a
can be
one of
combination
many.
as well.
But it's not just amplitude, right? So really, right, in digital, there's only amplitude.
Right.
Okay, but in analog, you could have amplitude, you can have frequency, you can have phase, or a combination of.
So we
instead
can
of just,
say
yeah, go ahead, Rana.
we can say it's 2 to the power of a single signal variation, regardless
right.
of how this variation is implemented.
That's right, precisely.
Okay.
Okay, so get this sort of definition sort of clear in your mind. Okay, so how do we do this, right? And I'm going to give you a break. I just want to give an intro to it. Okay, as I already said, right, we want to transmit an analog signal, and we have many tools actually, because the sine wave that we use, right, as the base fundamental signal for transmission, has 3 dimensions associated with it, which is amplitude, frequency, and phase. And we've shown that we can use high and low amplitudes for the transmission of data bits. We can use different frequencies to do that, and we can use different phases. Or we can also use a combination of this, and in particular, we use the combination of amplitude and phase. Not frequency, because we don't have control over frequency, because we have to buy frequency. Right? But from an engineering design perspective, we can obviously change the amplitude and we can actually change the phase. But we are bounded by how much frequency that we have paid for. So we don't usually change that. So the idea with sort of digital to analog is, okay, I can use one of or some combination of these parameters. And we call this, right, amplitude shift keying, ASK, because really, right, all it says is we're trying to shift the amplitude to denote something, to key for something. We're trying to shift the frequency to denote for something, and we're trying to shift the phase to denote for something. Or in one particular case where we use amplitude and phase, we call that QAM. And QAM is the most widely used mechanism now because it offers 2 degrees of freedom. I can change simultaneously both the amplitude and the phase. And the question then should have in your mind is, how do we even represent that? Is that clear? Okay, so we'll take a 10-minute break here. Okay, we haven't taken a break actually since the quiz, right? So we'll take a 10-minute break here. Okay, and then we'll come back and then we'll go through each of these different techniques. Okay.
Sounds good.
Resume 11:35. Is everybody back?
Yeah.
So before the break, right, what we were sort of talking about, right, was that, okay, if I want to now represent digital as an analog sort of a signal, then my goal is obviously to exploit, right, the different parameters that the sine wave provides me with. Right? So there is obviously the amplitude that I can change, the frequencies I can change, and obviously the phase that I can change. And if I want a greater degree of freedom, then I can change both A and P at the same time. Right? And we call that quant. So let's take a look at them individually. So in ASK, it says this, right? I'm going to change the amplitude to denote for something. Which means I only want to change the amplitude, but keeping both the frequency and the phase constant. This is what it looks like. Take for a second just to absorb this. I'm saying this, Shankai, if I want to transmit to you, right, the logical ones and zeros, I'm going to transmit logical 1 at a certain voltage, and then I'm going to transmit logical 0, right, at a 0 voltage. Does everybody see that, in fact, what this looks like, right, is now 1, 0, 1, 1, 0, high amplitude, low amplitude, high amplitude, high amplitude, low amplitude. Does everybody see that? So effectively, right, the frequency is still the same. What I've done is, right, I've effectively forced the voltage of this logical 0 to 0. But in fact, there is still a carrier frequency associated with it. So let me ask a slightly more extended question here. If you take note that there is a bit rate of 5 bits here, so there's 5 bits here, all in 1 second, so the bit rate is 5 bits per second. There's obviously 5 different signal elements, 1, 2, 3, 4, 5, also in 1 second, so the baud rate is 5 seconds. Can anybody tell me what is the carrier frequency used in this particular signal? What is the carrier? Because that will play a very important role in for you to answer question 1 is an assignment 2. What is the carrier frequency here? How do I determine the carrier frequency?
No, I think it's the high frequency.
Higher frequency, right? So obviously there's a carrier here, right? There's a carrier frequency that's carrying the signal. And my question is, what is this frequency?
Is it 5? Because there's like 5 bits there?
No. You do have to use the 5, but it's not as simple as that. Remember, right? You're always referencing with respect to 1 second. So this whole duration time frame here is 1 second here. Can you determine, based on this diagram, which obviously you can, what the carrier frequency is here in this problem? Anyone? No. You're very close, Yongju, but it's not 9. Remember, I said this, right? The frequency and phase remains constant for all of these signal elements. The reason I got to this 0 straight line here is not that the frequency is 0, but the amplitude is 0. So, Yongju, would you like to revise your answer? No. The frequency here is the same as the frequency here.
Is it 15?
15, exactly.
Okay.
Does everybody get that? Essentially, right? What I'm saying is this, is that the carrier frequency is actually carrying the 1s and 0s, right? There is now 3 hertz. Actually, I shouldn't say it's 3 hertz, but there's 3 cycles here per each of these signal elements. So if I extrapolate this across 1 second, which is what this time duration is 3, 3, 3, 3, 3. The total number of cycles in 1 second is actually 15, and therefore 15 hertz. Does everybody follow?
So the 0, it doesn't mean like, we're not transmitting anything.
No.
It is not reaching that amplitude, but I'm still transmitting at the same frequency.
That's right.
Okay, got it.
Okay, I'm still transmitting at the same frequency. I haven't changed that. In fact, right, the next slide will show you how this signal is actually produced. Okay, so it's important, right? So at the end of the day, right, your goal in question 1, assignment 2, is to draw a signal of sorts to represent a certain bit stream. And obviously, right, you need to take into account what the carrier frequency is, what is the bit rate associated with it, right, and so on and so forth. Okay, and this gives you a foray into that, is that this is 5 baud because there's 5 different signal elements. The bit rate of 5 because you're carrying 5 bits, you're representing 5 bits, and uses a carrier of 15 hertz. Because remember, right, the only reason why this is 0, remember the base sine wave equation, right, is y of t equals to a sine, right, 2 pi ft plus theta, right? I haven't changed this, and I haven't changed this. What I've done is I've changed this to 0, and therefore you get a straight line. And that's how this particular signal element is actually created. Is that clear? Okay, it's important that you understand this, right? And if I give you some insights to how this is actually created, right? First of all, this is digital, okay, and some definitions here, right? This is the incoming, This is the incoming signal, okay? This is a 1, a 0, a 1, 1, 0, right? This is in digital. Remember, I'm going from digital to analog. This is the carrier. It's actually doing 15 oscillations per second. Okay? What I've done is that I've used a multiplier to say this. Okay, in a logical 1, I'm going to allow the amplitude to pass through. In a logical 0, I'm going to force the amplitude to 0. Right? And I'm going to let the amplitude pass through, and then I'm going to force the amplitude to 0. So what I have now, right, as a transmitted signal, right, is high, low, high, high, low. You don't really need to know how it is obtained, however, but the hardware sheds a lot of information and insights, right, as to how this modulated signal is actually created. So some terminology, right? This information coming in, this is digital. Can anybody tell me what type of digital scheme this is? What's this line coding scheme here?
Unipolar?
Unipolar, yeah.
Return to 0 or non-return to 0?
Non-return to 0.
Exactly. It's a non-return to 0. Okay, you should be able to pick that up right away now, right? This is a unipolar because it's only positive 0 and positive E and 0, right? And it's a non-return to 0 because there's no change in between. This is what I mean by linking everything together, right? So your next week's quiz may be a problem of sorts where you're now pulling everything from before and trying to solve a problem. Okay, so it's not intended to be a trick question or anything. The intent really is this: I'm giving you the information, and I'm hoping that you can extract the necessary information to solve the problem. Is that clear on what to expect for your quiz next week? Okay. Any questions on ASK?
Can you repeat that again?
No. So I'm saying this is that I might give you a signal, right? And the signal could be a unipolar type of a question. Right, unipolar non-return to 0, right, and I expect you to be able to identify that because we'll see shortly.
Okay.
Yeah, it's pulling everything from the past. It's not just isolated to that one module, right? Because the knowledge is cumulative. Okay, so the important thing now is terminology. This is line coding, right? This is the carrier, and then the signal you transmit is called the modulated signal. Be very clear because assignment 2, question 1 also asks for the modulated signal, which is the actual signal that you transmit after modulation. Okay, now let's look at FSK. What did you miss, Chantal? The modulated signal? To add what? Sorry. You're not adding, you're multiplying. You're multiplying this by this, This is your line coding scheme. You're multiplying it to oh, I see. You mean for the assignment. Oh, I see. Okay. No, but that's for the assignment, right? And but the assignment is not ASK though. Right? The assignment question is not ASK. Okay. So let's get through all the schemes first, right? And then we can sort of relate this to the assignment. So in frequency shift keying, right? The idea now is that I'm going to change the frequency component of the signal, right? And I'm going to hold the peak amplitude and the phase constant. So let's take a look at this. Does everybody see that the amplitude is constant? The phase is also constant. But what's changed, right, is the frequency of the carrier signal. Right? So the bit rate is still 5. The baud rate is still 5. We're still transmitting 5 bits. But now, right, instead of squashing the amplitude here to 0, I'm actually slowing down the frequency here. So this is 4 hertz. This is 2 hertz. This is 4 hertz. This is 2 hertz. Can anybody tell me now what's the carrier frequency here?
Is it 20? Right.
Absolutely
16. Yeah.
no. Maybe. Why did I say maybe? So I'll say this: it's either 20, or it's 10. Why? It's definitely not 16. So it's either 20 or it's 10. Right? How do we get 20? Well, because it's
4 times 5.
How do I get 10?
2 times 5.
2 times 5. Because I haven't told you, in fact, which one was sped up and which one was slowed down. I could have used the carrier of this guy and speed it up for 1. What I could have used the frequency of 20 and slowed it down for 0. Does that make sense? I just know that I'm changing frequency, but I haven't told you, in fact, am I speeding up or am I actually slowing down depending on the logical value? So the implementation will shed some light to it. In this case, right, the carrier frequency is actually 10. Because what I've said is this, is that if I have a high, which is a logical 1, I'm going to use this through what we call a voltage control oscillator to speed up the oscillation. So my base is actually 2, right, per cycle, which means over 5 symbols is actually 10 hertz.
Can you repeat that, please?
Yeah. So what I'm saying is this, is that I'm speeding up because of a high voltage. My carrier is actually 10 hertz. But if I have a high voltage, I'm going to actually speed it up. If I have no voltage, I'm going to now transmit only the carrier frequency, which is this guy here. Do you see that? The reason there's a yeah, go ahead.
You know that because of the middle line right here, right?
Which middle line?
Between the digital and the converted signal?
Yeah, exactly. Yeah, exactly. This is your carrier. And I'm saying that the reason how I change, remember, in FSK, I'm only changing the frequency. Right? And how I change, I haven't told you. You just saw the effects of this is the modulated signal. This is what's being representing 10110. And I said that it could either be 20, which means that I've slowed down from 1 to 0, or I've sped up from 0 to 1. So in this case, right, the implementation actually shows you that, in fact, I use a VCO, which is a voltage control. So the higher the voltage, the faster you oscillate. So my base carrier frequency is actually 2 per cycle, which means 10 hertz. And how I denote a logical 1 is that I sped up double. of the base. And then I went back to the base. I sped up, and then I went back to the base. Is that clear? But the important thing for you to note here is this, is that the amplitude and the phase remains the same, right? This is phase 0, this is phase 0, this is phase 0, right? So is these. Oh, no. So it means this is higher oscillation respect to this. Do you see that, Yongju? Yeah. And it comes down to how it's implemented. That I will tell you. You don't need to know that. So the question when I ask you here, right? In fact, you don't know what the carrier frequency is because I haven't told you how this modulated signal was actually generated. I haven't told you that. The only way you can find out is if you know and you see this diagram here, is that, in fact, with a logical 1, I've, in fact, sped up on the frequency. Okay, Yongju? Okay. Then the next thing I want you to be aware of is this. This is called a coherent signal. Right? It's coherent because the amplitude for each bit, right, is constant, right? Obviously, that's given. But what's important is the phase. The phase continues on smoothly. So it ended at 360 and then it continued on to a 0. It ended at 360 and continued on to a 0. It ended at 360 and continued on to a 0. Does everybody see that? So
Yes.
This phase is continuous. Okay, we call this coherency. Okay, a non-coherent signal obviously is when the phase changes, and you would expect that obviously in a phase shift keying. This is incoherent or non-coherent, right? Why? Because it ended at a 0. Sorry, ended at 360 or 0. Doesn't really matter. Okay, and then it started at a 180. Does everybody see that? This is not. This is incoherent. Do you see that? Because there's a change in phase. So in phase shift keying, really, right, what happened is this. I'm now changing the phase, right, to represent the different elements. 2 5 bits, 5 odds. But how I represent it is now, they're all the same frequency. There's 3 cycles here, 3 cycles here, 3 cycles here, and so on and so forth. Right? But what's changed to represent this is Shankai is measuring, oh, are you starting at 0 phase or are you starting at 180 for each of these symbols? Right? And it's clear here, right? The carrier frequency here is 15 hertz. Does everybody see that? Because it's 3 cycles, right, per each of these bits, right? A total of 15 per second, so 15 hertz. So how do I generate this? Right? And obviously, these are just sort of the advantages and disadvantages of it that we talked about. Right? How do we generate this? We actually now use not a unipolar line coding scheme. What is this? Is this polar or is this bipolar?
Polar?
Polar. Okay.
Exactly, because it's a plus and minus V. Okay, and why is that the case? Because if you look at this now, right, a minus to a sine wave effectively is 180 degrees phase shift. So basically, all I'm saying is I'm multiplying this polar scheme now to take on the negative value so that it actually flips the sign of this. And the net result of the modulated signal, which is what I transmit, is now a non-coherent signal, right? Where I have now a 1 at 0 phase, a logical 0 at 100 degrees phase, right? And so the 1 0 1 1 0. Is that clear on how I achieve sort of the FSKs, PSKs, and then the BSKs? Any questions? Any questions here?
Maybe later. I'm processing right now, so.
Okay, good. Okay, so keep that in mind because we're not done. We still have one more to go, right? The question is this, right? I've now been able to change the amplitudes. I've been able to change the frequencies, and I've been able to change, obviously, the phase. And they all have their pros and cons, right? The pros and cons are as what we have discussed previously, right? PSK, right, really doesn't take amplitude into consideration. It doesn't really matter, right? PSK doesn't require multiple carriers, right? And so on and so forth, okay? The important thing now is this, right? With 1 degree of freedom, the amount of different signal elements I can create is limited. True?
Yes.
Because I can only change the amplitude, and I'm capped by the power that I have assigned to it. I can only change number of frequencies, and I'm capped by the amount of bandwidth that I purchased. And I can only change in phase, right? Which obviously, right, I'm bounded because it's total only 360 degrees that I can actually use. True? So how can I get more degrees of freedom? Well, maybe I can consider using more than one parameter. This is what QAM does. In fact, I change both the amplitude and the phase. Okay, so what I'm trying to get here now is this. How do you think I can actually achieve that? How do you think I can achieve that? How do you think I can simultaneously achieve both a change in the amplitude and the phase? And how do I represent that? Anyone? Okay, so I'll illustrate this for you, but before I get onto it, right, I'll just tell you, it uses two carriers, but they're the two carriers of the same frequency. Be very clear with that. I'm not using another frequency. So a carrier obviously has one frequency. I'm saying I'm using two carriers. Okay, but these two carriers are differentiated by the fact that they're 90 degrees out of phase with each other. We call it one the in phase and the other one the quadrature phase. Okay, so I'm going to illustrate for you on the whiteboard. Okay, so I want you to pay attention to this because this is really important. Okay, effectively what I'm saying is this: is that to represent a change in both amplitude and phase at the same time, I'm going to use two different carriers. I call this the in phase component, and this is the in phase amplitude. Okay, it's in voltage. Okay, then I have 90 degrees apart. Remember, right? On a unit circle, do you guys remember the unit circle? Right, it goes like this: quadrant 1, 2, 3, and then 4. Do you guys remember this? Okay, so this is 90 degrees apart. This is the quadrature component. And then obviously I care about the amplitude. And it's also in volts. Okay. So what does this mean, really? It says this: okay, I want to be able to change both the amplitude and the phase of a signal element at the same time. So how do we achieve that? In fact, how this was actually achieved is actually quite ingenious. And this is the underlying sort of technology for the high data rates that you guys see these days on Wi-Fi 802.11ac in LTE systems and so on and so forth. In the in phase, right, I usually represent this by transmitting a cosine. So a cosine looks like this. Right, this is a cosine signal. Let me just remove the axis, right? I just want to do a cosine here. Does everybody see that this is a cosine? And in the quadrature phase, I transmit a sine wave like this. So cosine and sine are shifted by 90 degrees. Okay, so how do I represent this, right? Usually I can transmit a cosine 2 pi ft here, where A is the amplitude. And in this particular sine, right, I can transmit a B sine 2 pi ft, where the f is the same f, because they're the same frequency, but they're 90 degrees apart. And they're 90 degrees because one's a cosine and one's a sine. So why is this really ingenious? It says this: I'm going to now transmit 2 carriers, but they're the same frequency. I'm not using another frequency. Remember, frequency is actually very expensive. But I only need to manipulate the values of A and B. What do I mean by that? In the in-phase component, I'm going to transmit A. Amplitude of A, right? So this is amplitude of A. Okay. In the quadrature component, I'm going to now transmit the value of B. What the receiver gets, obviously, is both of these signals. Which is this. The receiver gets this particular symbol here. This is a symbol. This is a signal element. The question now is this, is that what is the amplitude of this symbol and what is the phase of this symbol? Okay? The amplitude of a symbol is always measured with respect to the origin. So this is the origin, right? Remember, this is what I transmit. This is A, and then obviously this is B. So the amplitude of this guy here really is this. Do you follow? From the origin to the symbol. And I can call this, right, the amplitude of the symbol. A of S. Does everybody see that? So how do I determine the value of A of S? A of S equals to?
A squared plus B squared square root?
Exactly. It's simply Pythagoras, right? It seems complicated, but it's really just Pythagoras, right? This is a right angle triangle here, right? The value here is A. The value here is B. So this value here is the square root of A squared plus B squared. And then in volts. Because it's a hypotenuse. Does everybody see that? So that is the amplitude. What about the phase? The phase is this parameter that I'm trying to get here. Phase of S. Okay. What is the phase of S? Do you guys remember from, I don't know, grade 10, something known as SOHCAHTOA? Yes. Is this a SO or is this a KA or is this a TOA? Right. So Yongju, you could use sine of that, right? But the reason you don't do that, right, is because, right, and it's not this, it's actually B, right, because it's opposite over hypotenuse. Okay. But this is your unknown, right? A of S is unknown, so you don't really want to do A of S. What's being transmitted is actually A and B, exactly. So really, the angle is really just tan, right, inverse, right, or arctan, right, of opposite over adjacent, which is B over A. So the result of this, right, is very complex, right, in terms of the derivation of it. Okay, but the derivation of this is actually more complex because it uses a bit of trigonometry. But as I said, you don't really need to know the derivation, but what you do need to know, right, is the result of it. Is that now, if you start to see this, previously I could only change amplitude, I could only change frequency, I can only change phase. This is called QAM, right? And it gives me the ability to change. And in fact, if you look at this two-dimensional grid, I can put a symbol anywhere on this two-dimensional grid. This is usually the in phase, and this is the quadrature phase. Simply by defining what the amplitude is on the A and what the amplitude is on the B, which is your cosine and your sine wave. So you get all of these intersection points that can happen. right? Depending on which values you actually choose. And these are effectively your symbols. And I can put a symbol anywhere. I'll give you some examples in a second here. But is that clear on how we can actually determine what A of S is and what the phase of the symbol is, based on the transmission of an in-phase component and the quadrature phase component? Is that clear? There's a moment of silence here, right? I'm not sure if you guys are following or you're not following.
I kind of understand the phases. I still need some time to process the because I don't think I ever get in contact with the TOA call and solving. So
Okay, yeah, no. So basically, just says this, right? Is this angle here is the opposite over the adjacent, so it's B over A. So
okay,
TOA doesn't. Yeah,
that one I understand. Yeah, that one I understand.
Exactly. That's all you need to know. You don't really need to reproduce this in a sense that I don't need you to derive it.
Oh,
Okay.
okay.
Okay, but I do want you to know how we can change both the amplitude and the phase. Remember, right? If we go back to our screen share, right? I said that what QAM allows us to do, right, is we want to change effectively both the amplitude and the phase at the same time. Okay. And it may seem complex, but what this complexity does give us, right, is a very elegant solution. The solution is very elegant. Amplitude is defined as just the square root of the sum of the squares of the amplitudes. Right? The phase of the symbol is simply just the arctan of B over A. And this technique allows us to put a symbol anywhere on this grid system. So what does that mean? When the receiver receives this, it can say, okay, I received 0, 0. If I receive this, is 0, 1. If I receive this, this is 1, 1. Right? If I receive this, right, this is 1, 0. Does everybody see that?
Right. It's like are they in like a same amplitude, like for like quadrant 1 and quadrant 2?
Yeah, the same amplitude. But this one obviously is a negative A in quadrant 2. This is a negative A, right?
Right.
So this here is a negative A. This is a positive A. Okay, so what is the general rule of thumb here? Okay, the general rule of thumb is this, is that when you design and this is a signal constellation diagram. Okay, the general rule of thumb is very simple. You want all of the symbols to be as close as possible to the origin, because it means that you're using the minimum amount of power. But at the same time, you want all of these symbols to be as far apart as possible from each other. Why? Because if I have a system that looks like this, and it's still 0, 0, 1, 0, 1, 1, 0, 1, the room for error is very small. If I receive something here, I'm going to say this is a 0, 0. If I receive something here, right, I'm going to say this is a 1, 0. As opposed to this, right, I have much larger rooms for error. Because remember, right, these are amplitudes, and the amplitudes are still going to undergo attenuation and perturbation in transmission. Okay, so if I show you some diagrams here, okay, if I show you some diagrams here, 1 second, let me load it up here. I'm showing you, wait, hold on, I need to share this diagram. Cancel this screen share. Can you see this diagram?
Yes.
There is 256 QAM versus 1028 QAM. So 256 QAM just means that there are 256 of these symbols. And each of these symbols carries 8 bits. Because it's 2 to the power of 8 gives you 256. So this one could be 0, 0, 0, 0, 0, 0, 0, 0. This could be 1, 1, 1, 1, 1, 1, 1, 1. Now, this is 1024 QAM. Because there's 10 there's 1024 of these symbols. Each of these symbols will carry how many bits? Anyone? 10 bits, exactly. This will be 00000000000, right? At this corner here, this could be 1111, 1111. Can you tell between 256 QAM and 1024 QAM, which is more resilient to noise? No, the bits, the bit indication is not standardized. You basically want to use it doing what is known as gray coding. Okay, so I'll define those for you. Okay, but if you look at these two diagrams here, right, 256 QAM, right, versus 1028, which is more resilient to noise?
256.
Why?
Because you have more rooms for errors.
Exactly. Does everybody see that? Precisely, that's what it is. Okay, and what mathematicians have been doing for their entire lives is to try to design these type of signal constellations, right, that are as tight as possible to the origin, because obviously every symbol requires some amplitude to transmit. So the tighter you are to the origin, the less amplitude you use. Yet you want to get maximum separation, right, between the symbols. Okay, I'll give you an example. So the state of the art right now, right, you may be surprised, right, is 1024 QAM. Your LTE systems are using 1024 QAM, 10 bits per symbol. Okay, and you might think, okay, well, it's not that much more than 256, but it really is, because from 8 bits to 10 bits, you've gained 20%. In fact, from 8 to 10, you've gained 25%. Does everybody see that? Because every symbol you transmit is not just 8 bits, right, but 10 bits at a time. You've gained over time, right, you gain 25% in throughput. I'll show you another diagram. Take a few seconds, read this diagram. What can you say about this diagram? What does it mean? Doesn't look accurate.
The 27 SNR
Yeah.
is more susceptible to noise. So noise is it's difficult to get the signal out from the noise in the 27, where it's way easier in the 37 one.
Exactly.
It's more accurate in the 37 one.
Exactly. This is an actual received energy of the symbols coming at the receiver. So remember, right, high SNR is good or bad?
Good.
Good, exactly. So in a high SNR scenario, right, and this is about a 10 dB sort of increase, right? You start to see this, is that in a high SNR situation, okay, what happens? Well, everything received, it's in its proper position because the signal strength is much higher than that of the noise. In a low SNR comparatively, right, you start to see now, because the noise can obfuscate the received symbol, the symbol no longer lies in the position it should be. It could sometimes go across its boundary and go into and misinterpret. So on your cell phone, this is 5 bars. SNR equals 37 dB is actually 5 bars. On your cell phone, this is likely 2 bars at 27 dB. So what does that mean? How do you solve the problem? If let's assume, obviously, you have no control over your signal to noise ratio, true? You don't have control over that, right? Because anytime you're on a wireless device, right, your environment is not controlled by you. I mean, you could try to manipulate it by walking closer to the base station, but that's really as much as you can do. So what do you think happens when you're in this situation? Do you want to receive data with lots of errors? Does everybody see that this, if you get something like this is data with lots of errors? Because all of your symbols, right, could be crossing its intended boundary and be decoded correctly as the wrong code. So how can you do to prevent errors if you're in this type of SNR condition? What do you want to do? So without using the problems, what is your plan? What do you want to achieve? Or what do you plan to do?
Transmit less data.
Transmit less data, which means effectively what?
Like reducing the bit size?
Yeah, exactly. Reduce the bit size because it goes down to a lower QAM, right? When under the same power condition, just like what Shankai is saying, right? So this is 256. If I go down to 128, have I effectively increased the distance between symbols? Right? Just like when I showed you this, right? If I have a system, right, that is doing 1024, right, and it's getting lots of noise, I could effectively bring it down to an 8-bit system. Have I increased the spacing between symbols from going down from 1024 to 256? Does everybody see that? The distance between symbols is greater here, right? On the left as compared to the right. Is that true?
Yes.
That means more resiliency to noise. True? Because
Yes.
this symbol now can move around a lot more without being misdecoded. And that's why on your cell phones, right, there is something known as adaptive modulation and coding, AMC. I'm constantly trying to adjust the system I'm using to ensure that I have very low errors. The cost is lower data rates. So as an end user, right, when you're on high, like 5 bars, you have very high data rates because you can transmit at the highest possible system, 1024 QAM. So 10 bits per symbol. But if you go into an RF condition, right, where SNR starts to drop and you're dropping from 37 to 32 to 27, right, and so on and so forth, instead of trying to get errors, you will reduce your signal constant. This is called lower order modulation. You're going down from 1024 to 256 because you want to increase the spacing, right, so that you're not getting errors, but your data rate now drops. So you might be on a gigabits per second system, you drop by 25%, right? You're now at a 750 megabits per second system. So 20% is significant. 25% is significant, right? You've gone from 1 gigabits down to 750. Okay, does that make sense? So, okay. So what are sort of the mathematicians and engineers doing now, right? Just to give you some foray into what they're actually doing, right? They're trying to create for obviously your next generation systems, right? Port 4096 QAM. Okay, and why are we able to do this? Okay, so in order to do this, right, we've gone from 10-bit systems to 11 bits and then to 12-bit systems. Okay, why are we trying to do this? Simply because we want to increase the data rate. It's another 20% increase. Okay, but that would require now to have 4,000 symbols to be generated. Okay, is that clear? Okay, so if I go back to my slides, right, let's just formalize this a little bit. Okay, so this is QAM, right? And what we do with it, right, is because we want to okay. The idea of QAM is that I want to increase the degree of freedom, right? I'm going to now, that's a lot, exactly. Okay, 4096, right? And in fact, we're trying to move into 8192 as well, Zikai, just so you know. Okay, we're going to a 13-bit system. Okay, and you may think that that's insignificant, but that's another 30% increase, right, relative to what we have today. Okay, but it means that we have to control power and we have to control noise, or we have to eliminate the noise, right, so precisely that we're not getting bit error rates. So what do you think the next sort of deployment? You might, so some of you might have already read about it. In fact, going forward, right, your Wi-Fi deployment system at home is not going to be the same deployment as you have right now. Effectively, right, you have transmitters in every single room of your house, because what they need to do is that they need to go very, very short distances at very, very high power in very short bursts, right? Because they're trying to go into a system that's 8192 QAM. So instead of trying to get through all the attenuation of the impairments, right, what your deployment system will require you is that you're going to have a little access point, just the access points, in every single room, right, they're trying to connect, right? It has already been said, right, that 5G, right, in terms of cost of deployment, will be the most expensive cellular deployment to date. In fact, it will exceed the cost to deploy, right, all of 1G, 2G, 3G, 4G combined. Because you will now start to see cellular antennas on every floor, on every room, right, of buildings, depending on how they're actually structured. Right? And we're going to see that happening also to the consumer space, which means that no longer do you have one wireless router for your entire house. You're going to have one router, but possibly up to a single transceiver, which is the actual access point in every room that you're trying to have access to the network. So very short distances, very high SNR, right? Which means you almost have to have a direct line of sight, which means that everywhere you use the equipment for the high data rate should be able to see the transmitter. Is that clear, Zichang? Okay, and that's obviously the model that we're moving towards. Okay, and the reason, as you can see now, hopefully I show you some insights, is because we're trying to attempt to go to 4096 QAM and 8192 QAM. Right, which means that there is very little room for any of these impairment errors. Okay, so to wrap up on this deck of slides here, right, just really is formalization of what we just went through, is that now we have QAM, right? We use two carriers, the in-phase component and the quadrangle phase component, but they're using the same carrier frequency, so we're not using another frequency, but we're using the same carrier, but now these two carriers are 90 degrees out of phase. So we represent one, right, usually, right, using the cosine, and then obviously in the quadrangle phase, we used the sine. This gives us, right, just based on the values of A and B. Remember, right? Yes, we're transmitting sine and cosines, but we only care about the peak amplitudes of these two carriers. We care about the value of A and we care about the value of B. It will give me the amplitude of the symbol as well as, obviously, the phase of the symbol. Okay? So what are constellation diagrams? It's essentially what I just shown you here. Okay, what you want now, obviously, right, is that there are two axes, the I component and then the Q component. Okay, for each of these symbols, there are 4 pieces of information. Right, obviously the peak amplitude, which is in the I, which is what we call A, the peak of the Q, which is called B. And from here, we can deduce the peak amplitude of the signal element and the phase of the signal element, as we have shown here. So this is the IA, which is the peak amplitude of I, and the peak amplitude of Q. And this is the peak amplitude of the signal element, and this obviously is the phase. So let's take a look how we read signal constellation diagrams. Okay, I want you to take a look at these guys for a second here, because it's now going to make you sort of understand. So from a legend point of view, right, the prefix B just means binary. The prefix Q just means chord. Right, so 2 points, right, or 4 points. So 2 symbols, 4 symbols. Okay, these are the symbols. These are the signal elements. Right. Okay. So if you recall, right, in a unit circle, it goes from 0 to 360. Can anybody tell me why this is BASK, which means it's binary, 2 points? We see that. But why is this ASK? What is the definition of ASK?
Amplitude shift key.
What is the, by definition, what should ASK do?
Changes the amplitude to represent different signals.
And holding what constant?
Voltage. No, voltage is going to change.
Right. Holding what constant?
Phase and frequency.
Phase and frequency. So why, as a signal constellation diagram, is this a change in amplitude? Is there a difference in amplitude here? Because the amplitude is defined with respect to the origin, true?
Yes.
Is there a phase change here?
No, because it's not crossing. Sorry, it's not crossing to the left side here.
That's right. It's not crossing the origin.
Yeah.
Right? Crossing the origin equates to how much of a degree the phase change?
90 degrees?
No, crossing the origin.
Crossing 180, right?
180, exactly.
Yeah.
Okay, does everybody see that? What we cannot capture, right? What we cannot capture, right? Hold on, Chantal, I'll answer your question in a minute, okay? But what we cannot capture, obviously, is the frequency changes because the constellation diagram does not have, unless we have a third dimension. Okay, so this is telling us, right, that obviously is binary because it's 2 points, right? And it's ASK. Okay, why is this PSK? PSK is changing what? The middle diagram, phase. Assuming that the amplitude is kept constant here, right? It's the same distance to origin, the same distance to origin. This is PSK because why?
It's crossing the origin. It's going to the other side. So
Exactly,
the
which
phase is
means-
being changed.
Exactly. Okay. Why is this QPSK?
Changing both amplitude and phase.
That's right. Amplitude and phase. Why? Is there a change in amplitude?
Yes.
Are you sure?
Um.
If it's PSK, can you change the amplitude?
Oh wait, no, you can't, right?
You cannot.
Yeah, you can't.
So how can you tell that it's not changing the amplitude?
Because that line, should I say, call it that line, or like because they all have the same radius.
That's right. It all falls on a unit circle.
Yeah.
Exactly. Right?
Can you repeat that, please?
Yeah, because remember, right? This is a circle, right? This dotted thing here is a circle.
Yes.
Okay.
Oh,
If
so
everything
it's the
is-
same distance from the origin. Yeah.
Exactly. So you will not notice one thing, right? It's actually not that difficult to read this at all. Okay, and I'll show you why. Okay, because anything that is BSK, and I'm going to give you a summary here. I'm just trying to find a slide. Oh, I have no slides to use. I don't know why they restrict me to only 10 slides in every class. Okay, I can use this one. Can you see this one here? Okay.
Yes.
If in ASK, in a signal constellation diagram, right? Let me ask you: is this ASK? Or is this not ASK?
That is ASK because the length is different.
That's right. But is the phase the same?
Yes.
Yes, right. We're talking about relative phases of each other. So ASK has one easy secret. As long as you are on the same axis and the symbols are all within the same quadrant, then it's always ASK. This is ASK too. I can draw more of these symbols, right? Does everybody get that? This is ASK. Right, this is QASK. Right? PSK is very easy to identify because PSK always falls on some kind of a unit circle. True? Because the only thing that changes is the phase.
Yes.
But they always have to have equidistance to the origin,
Which is the amplitude.
which is the amplitude.
Yes.
So to answer Chantal's question, right? No, QPSK cannot be QASK. Right? Because this is QASK, and if there's only 4 of these guys here, this is QPSK. Because QPSK, right, is phase change, and QASK is amplitude changes relative to each other. that clear, Chantal? Okay. And then QAM, obviously, right, is simply just any positions that I want. But there is both an amplitude change
And phase change.
and then there's a phase change. Does everybody see that? So we use the signal constellation diagrams a lot because it is a very convenient way, right, for us to view these signals, okay, in the dimensions that we are concerned about. What about FSK? Anybody know how to draw an FSK? Actually, in 1 year in the midterm, I said, okay, there is a 32 FSK. How do you show FSK? So this is QAM, right? How do you show FSK? How do you draw a 32 FSK? So 32 means how many symbols? How many symbols are there in 32 FSK? Okay, how many symbols are there in BFSK? No, not 32. 32 FSK means 32, but what about B? 2, right? So how many symbols do I expect in 32? BFSK. I've changed it to BFSK now. Each symbol carries how many bits? Youngju? If there are 2 symbols, each
5?
symbol in 32 or in B?
In 32.
32 is 5, but in B it's
2 symbols, 1 bit.
1 bit, exactly. So how do you denote 32 FSK or BFSK on the signal constellation diagram? This was a past midterm question. I just said draw 32 FSK. Do all the FSK symbols have the same amplitude?
Yes.
Yes.
Do
They
all
have
of them
the
have
same phase. Yes.
Exactly. So in a diagram where you can only show amplitude and phase, where would these symbols reside?
One point.
1 point, exactly. So I can choose any point, right, depending on the amplitude and the phase, and they will all 32 will be on the same point. Does everybody follow that? Because the amplitude is the same and the phase is the same. What you really want to be able to do, right, is if you have a third dimension, right, that sort of cuts out, right, on this guy here, then you can lay them out in the frequency domain. But we don't have that in sort of the signal constellation diagram. Okay, very good. So I've shown you sort of the different QAMs, right? But it's just sort of to illustrate to you. Compare these 2 QAMs. What can you say about both QAMs? They're both 4 QAMs. Which one is more resilient to noise, A or B?
B.
B. Which one requires more power, A or B?
A.
More power? What is power? Right? The power is obviously the amplitude, right? The origin. If you add up all of these distances, which
It's
one
the
has
same,
more?
right?
They're the same. Yeah.
Not quite, right? Because the diagonal is always longer, right? This one is lesser power than this power. True? The
Oh,
diagonal
right.
is always
Yeah.
longer,
Right.
right? So the cost. Then
Can
go
you
ahead.
repeat that again, please?
Yeah, you remember, right? The power, right, is the distance from the symbols to the origin.
Okay.
Thus, the total distance to all of the symbols is B longer than the distance from origin to all of the symbols? Right? There's a distance here. there's a distance here, there's a distance here, and then there's obviously no distance here. True?
Yes. Yes.
Does the aggregate of the distances, is it larger in B as compared to A?
Yes.
It must be, right? Because we're using power, right, to make it more resilient. We're spacing them further apart from each other. Right? So B is more resilient to noise because there's more room for errors as compared to A. Right? But we start to lose that flexibility, right, as we go into higher order quants. Because we work in a finite power system. Right? And then obviously I show you, right, what we use today, right, which is 1024 QAM, right, 4096 QAM, and then we're trying to get 8192 QAM. Okay? And all because you guys demand higher throughput. Right? At some point, right, I think that the consumer has to start demanding that. Truly, do you need to watch your movies in 4K as opposed to 2K? Do you really need to watch your Netflix in 8K, Shenkai? So why are you asking for that? I mean, do you get any difference in viewing pleasure just because you get something in 8K versus 4K? So who asked for 4K? Chantel, do you ask for 4K? Right? So yes, why? Do you get a better viewing experience because it's in 4K versus 2K? Do you? Really?
Yes. Actually, there's a little bit of difference.
Right, but is it substantial enough though? Because look at the amount of data that 4K versus the amount of data generated by 8K systems versus the data generated by 2K.
And it's also limited by the hardwares too.
Well, forget about the hardware, right? But I'm just talking about data rate at this point. Let's say that all, right? So yes, I agree, right? It is noticeable, right? But is it required, right? We need to know, right, what's nice to have and what's actually deemed essential, right? All of that, what we ask for, right? There is a cost associated with it, right? And obviously, right, manufacturers wants to meet your requirements because they want you to spend more. But do we really need that type of a viewing experience? Obviously, that's really debatable. Okay, but my argument for you is from an engineering perspective, right? Is that the amount of energy that needs to be expensed to try to generate something at 8K, right? The amount of data bits that are being expensed to stream something at 8K, right? Perhaps if you were a designer of networks, right, your intuition, obviously, right, is perhaps not necessary, but just nice to have, right? Manufacturers will always push you to the latest and greatest because that's how you refresh your equipment. Is that clear? Okay, so always don't just put yourself sort of in the end user perspective, right? You got to think about the impact, right, of all of these requests. Okay. Any questions on sort of digital to analog? And Chantal, I'm not saying that wanting to see something nice is not is something wrong, right? All I'm saying is that there is a cost associated with it. Is that clear? Right, and the cost may not be most apparent to the end user. Right, there is a cost associated with it, and we need to be aware of it, right? Because you guys are in the field of technology, right? You need to not sort of really trade off, right? What does it mean to transmit something at 8K versus something at 2K? Precisely, right? To everybody, that's a different. That's why I say it's very debatable, right? Whether or not, right? So the Olympics that was supposed to take place in July this year was intended to be broadcast live in 8K, because the electronic manufacturers wanted to showcase, right, that if you can see every single pore, right, of Chantel, who's, I don't know if you guys are aware, but Chantel is actually an Olympian, right? She was supposed to participate in the Summer Olympics in Tokyo, right? The idea was that you could see every single pore, every single sweat gland, right, coming out from every single sweat coming out from a sweat glands. I am joking, yes, I am, but that's the idea, right? Is that obviously the manufacturers wanted to sort of push for the need and justification that you need 8K, And the only way that 8K can be any sort of noticeably different from 4K is that you can see every single pore and every individual, right, participating in the Olympics. And so is Melody. I don't know if you guys are aware that Melody is also an Olympian. Right, Melody? I see. Okay. Okay. Any questions on sort of digital to analog? Congratulations on that, Chantel. Any questions on digital to analog? Okay. So the important thing out of here, right, is this, right? There you go. See, we have so many potential Olympian candidates. And the question maybe I should ask is, what happened along the way that you actually now ended up in a career in computing? But in any case, right, that's for you something to do some retrospective on, okay? And I'll stop that before I become politically incorrect, okay? So digital is actually important, okay? Because what we really need to be able to do, right, is convert all this digital data that we're generating, and then we have to find some ways to transmit it wirelessly, okay? So that's really, really important. The other thing that I want to just go through, and this is a very easy sort of section here, which is called analog to analog, and we're only going to take a look at 3 different types here, right? So there's the AM, the FM, and then obviously the PM, okay? And they're very, very, very simple, right? Remember I asked you at the beginning of the class, right? I said, okay, if you have to do analog to analog, right? Why? 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 Anyone? No, it's not cost. Right? The answer lies in one of these diagrams here. This diagram. Why? Why do we want to do analog to analog?
So we can have more radio channels?
Exactly. So we can transmit multiple simultaneous streams, right, of information. Okay, it's not about accuracy. It's allowing the ability to not transmit everything at baseband. Okay, I'll give an example, right? AM radio. Everything you hear on the AM radio, right? Obviously, they're not identical content, but is it really, right? AM radio as in the fact that there's only human voice and instruments playing, right? In every radio station that you listen to, right? Really, right? What's being played on the radio stations are either human voice or some instruments playing. True?
Yes.
Right. So is the FM band, right? FM radio, AM. It doesn't really matter what it is. One is stereo and one's not. Okay. The truth is, right, if we play them all in the baseband, then obviously you cannot have multiple different channels playing at the same time. So you'll be stuck with one channel for life. I mean, can you imagine, Chantel, that the only channel you hear is the channel with my voice, and you're stuck with that for life, and you have no other options? How would that change your life? I take that as a compliment. But you can imagine, right? Obviously, right? Humans want choices. Human wants different contents, right? So obviously, I cannot just transmit everything in baseband. Okay, what I would have to do, obviously, right, is to say, okay, how can I take a service band like the AM band or the FM band, right? There's no PM band, but how can I take these bands, right, and then channelize it? And the answer lies very simply in A2A. Okay, so what is A2A, right? What we want to do is this, is that we want to use the carrier so that the amplitudes of the carrier matches that of the modulating signal. I'll show you. Oh, but the important thing, obviously, is that the amplitude, right, is the one that changes, and the frequency and the phase remains the same, just like ASK. So some terminology here. The modulating signal, right, is a signal that carries the information, just like line coding. The carrier is the one you transmit. The modulated signal is changing the carrier in some way. In AM, you're changing the amplitude so that it carries the information of the modulating signal. In AM, what we do is we create the envelope. Okay, we simply create the envelope. Is that clear? How do we achieve this? We multiply the two signals together. We say, okay, this is the signal. I want to have a higher frequency signal represent this. So I multiply this by this. And what I have now is that these are the changes in the amplitudes of the carrier. In fact, before it was all constant amplitude, but I've changed the amplitudes of the carrier by multiplying these two together such that this envelope here, if I trace this dotted line, this information is this. Does everybody see that? So the peaks of all of these carriers, if you connect them, will become the modulating signal, which is the data itself. Now, let's look at FM. FM is actually even simpler. We want to change the frequency of the carrier, okay? But we hold the amplitude and the phase constant. So if I have a modulating signal of sorts, right? So going from positive range to negative range, and I have a carrier applied. In the areas where there's positive amplitude, right? Remember, this is more and more positive. This is more and more negative, right? So this is positive amplitude. This is negative amplitude. As it becomes more and more positive, I speed up the frequency. As it becomes more and more negative, I slow it down with respect to the carrier. Right at 0, I transmit the carrier. How do you think I can create a signal of this sort?
Frequency shift key?
No, we cannot use frequency shift keying, right? Because this is not digital to analog. This is analog to analog. This is called frequency modulation, but we saw that, right? How do we change frequency with respect to its amplitude? We have a component called what? A voltage control oscillator, right? The more positive, the faster. The more negative, the slower. Do you follow that? Right? It just says this, right? I have a base carrier. At 0, I'm going to transmit the carrier frequency. If you're higher in amplitude than 0, then there'll be a speeding up of it. So at the maximum peak here in positive, this is the highest. At the lowest peak here, this is the slowest. Okay. In phase modulation, I'm going to now change the phase. Take a look at it. This is probably the more difficult one, actually. What can you say about how this PM signal is actually generated? How do you take the carrier and then go from the modulating signal, right, into the PM signal? Anyone? Does anybody see how this is actually achieved? No. Not quite, Yongju. And in fact, the answer is no. I'll give you a hint. It's got to do with the slope. Can everybody see that there is slopes here?
I cannot see anything. I don't know if the rest actually can see it.
Can you guys see it?
Yes.
Okay. This here, the first red line here, is that positive slope or negative slope?
Positive slope.
Positive slope. The next line is negative slope, true?
Yes.
And then the next one is positive.
Yes.
Okay. So the idea behind full modulation, and obviously it doesn't exist, right? There's no PM band. There's AM band, FM band, but there's no PM band, right? Because the radios were created about a century ago now, roughly, right? It's been a while since we had radios.
Your voice is breaking really bad now.
Okay, can you guys hear me?
Maybe
Yes.
if you can talk slower.
Okay, yeah. So remember, right? Radios have been created for what, a long time now, right? So if you look at this slope here, right? This slope here, okay, this is positive. In the region where there's positive slope, there's speed up of the signal. In the region where there's negative slope, there's actually a slowdown of the signal. And then when you go back to this, the positive slope here on the third line here, this is a speed up of the signal. And the signal, obviously, I'm reference to the carrier. Does everybody see that? Right. Positive slope, negative slope, positive slope. So speed up, slow down, speed up. Did you guys hear that? Okay. So the reason why, right, we don't have the PM band is because to find the slope, we need to do take what is known as the derivative. And in the early days when radio was first created, there was no easy way for us, right, to actually compute the derivative of a slope. And hence the PM band wasn't created. Okay, but it doesn't really matter from an academic study, right? We obviously can have, right, what we call the AM, right? The AM really is just trying to create the envelope, right, based on the carrier. The FM, right, is trying to take how positive or negative, right, the values are, okay? And then obviously the PM, right, is to now take care of, right, how positive or how negative the slopes, which is the derivative of the modulating signal is, and then represent that, right, with reference to the carrier signal. Okay, and that's really all I need you to know in terms of the A2A. Okay, so to recap, right, before I end the class today, right, we have gone through obviously A to D and D to D, right? So that was last week. And then we're going through, obviously, D2A and A2A, right, this week. So you know all four permutations of it, okay? So the question now is your assignment, right? Are you guys comfortable with getting this done for your assignment for Wednesday? Rana, are you there?
Yes, I'm hearing. I'm listening.
Yeah. Are you comfortable with getting this done for the assignment by this?
I'm going to give it my best shot. Is it going to be done? I don't know, honestly.
What does everybody else think?
I think I need to review this several times before I would be able to actually confidently implement it. Before I gain enough confidence to know what I'm doing.
Okay. Do you guys want more time?
Preferably, yes, because I think what I'm struggling right now is probably reviewing the notes for this lecture first, and then same with what Ron.
Okay, so we'll do a 1 week extension to it.
Oh, perfect.
Okay, so what that means is, so it's I don't want to extend it by 2 days or so, because what I want is that you have access to me again next Saturday. Right, so extended by a day or two really is meaningless to me because you don't really get time to ask me questions if there are any. Okay, but the extension is so that you are spending time to understand and being able to do the problem.
Perfect.
Okay, so we'll do a 1 week extension, but that means that there will likely be no extensions to any of the other assignments only because of time interest, right? We have 12 weeks total.
So depending on your knowledge, any other assignment is going to need an extension?
No. I've actually very rarely given extensions. Very rarely. The time I've given extensions in the day school, in fact, I've never given extensions ever in the PTS course, right? But I've given extensions in the day school only because at times, because they take 7 courses at the time, and what happens is that sometimes they have conflicting deadlines. So I set my dates early in the term. But the problem is that sometimes there are overlapping deadlines on the same day. So I tend to move it, by a couple of days sometimes, so that students get a bit more room to work on the assignments. Okay, but in PTS, I very rarely do that because we're in a very time box situation. Okay, do not forget though, right? You have a big project that you may have to do. So don't disregard that, right? So you still have 4 assignments, and if we go with no final exam, meaning that we're not using sort of the tools, then it will be a project, and the project obviously would be quite substantial. And you'll be given about 4 weeks to work on the project.
I think for me, it's like the graph that previously presented. I still need to go over that. That might take some time.
Right. No. I'm fine. I'm fine with giving you the extension, but I want you to be aware of the workload that you have, right? So oh no, the project will be I don't know. I think it should be individual, right? Melody? Right, it should be an individual project, right? Because if you get a project, right, it will be in sort of in lieu of the final exam. And I'll probably know and be able to let you guys know by the following week whether it will be a project for a final exam. And I'll tell you why. Because next week there will be a webinar for us, like instructors, right, on what's called the proctorial tool. So there has been many enhancements done and so on and so forth, and there will be an actual sort of walkthrough showing sort of the tools and the capabilities and advantages, disadvantages. It seems that BCIT is still latched on proctorial, right? I know, but there's been many things that are being done to it. So I'm attending a webinar next week on proctorial, understanding the latest sort of version of it, the capabilities, and obviously the disadvantages. But it's beyond my control though, right? Like I will tell you guys this, right? The number of tools that I have for me to administer a final exam is very limited.
So
yeah.
Can we compromise, and maybe everyone can actually give their feedback on it. It doesn't have to be a whole week, maybe less than that, so we can save up some time should we need that time moving forward. And in addition to the less time, maybe you can give us some insights on how to approach.
No, so what I can do, I think the better way actually, Rana, is that what I can do is I can actually release assignment 1 on Wednesday. Assignment 3, sorry. I can release it early.
Okay.
Right? So it doesn't impact your deadline. But I'm just giving you extra time to work on this assignment.
Okay.
Does that make sense to you? So the timeline to
if I'm focused on assignment 2, then even if I get assignment 3 early on, and I don't know the knowledge that I need to start with it, then I don't know.
Right. No, but the thing is that you should still be targeting, right? So I'm giving you an extension just as a courtesy. You should still be targeting to get it done by Wednesday. But in the event you don't, right, then obviously you still have more time and ability to ask me questions next Saturday.
Okay.
Right. So what I might do actually, maybe what I should do is just extend it to next Monday rather than a full week extension. We'll just get it done on the Monday. Really, the Saturday is for you to just ask questions.
So what does everyone else think about that?
Is that okay for everybody else?
I think it sounds good.
Yeah, exactly. So it's a courtesy extension that does not impact the timeline of everything else. Right. So, but I do want you to be aware, right, that yes, you still have your weekly quizzes. We're at week 6 now, so we're halfway through the term, right? From next week or the week after, I should be able to let you know precisely, right? But your major deliverables for the course, in addition, obviously, to your quizzes, right, includes 2 more assignments and potentially 1, obviously, project. Okay, so you're aware of that. In the next 6 weeks, you still have 2 assignments and 1 project to do. Is that clear?
Yes.
Okay, so I want you to be at least aware of that. Okay, so you're not sort of taken by surprise, right? If that shows up. Okay, but I'll get a webinar by the folks that created Proctorial next week, right? To really tell us how to mitigate around the issues and the common complaints around sort of Proctorial and so on and so forth. So once I get through with that, right, I think we will make it, because this doesn't just impact, you guys might have probably heard, right, is that Oh no, I hear you, Chantel. Right? We'll make so the issue is this: is that we are also moving online for the fall. Right? You guys are probably aware of that, right, Chantel? Okay, and it is becoming quite binding in terms of constraints, right? Because we don't have all the tools necessary to be able to proctor, right, an individual exam. Do you understand what I'm saying, Chantel? Right. So the institute, right? Right, but major assignment does not guarantee individual work. Right. That's the problem. Okay, and this institute actually has a very strong focus that you are actually achieving all of these learning outcomes yourself, and not through the help of every. So obviously, right, we want you to collaborate, but we want the work that you do to be representative, right, of the learning outcomes you have achieved, right? So it's a trade-off between that. Okay, so leave that to me. Don't worry about it now. Your focus now is to get assignment 2 done. Okay, Chantal. And then as I get more information, right, I will sort of disclose that to you guys right along the way. Okay, there's obviously a major push because we are primarily going to be online also in the fall, with a few exceptions to some like trade schools where they need to use machineries at BCIT where they'll be allowed back on campus. Okay. So nothing's changed. What I'll do is I'll make a date change. Again, I said I won't extend it to the following Wednesday, but I'll extend it to the following Monday. And then what I'll do is instead of bothering you with another assignment, I'll assign the next assignment on the following Monday. And then you still get the time frame that you guys will get. Okay?
Sounds good.
Awesome. Okay, thank you, everybody. Right, please review this information. Right, I hope you find the insights that you see, right, somewhat enlightening. Right, when you use your cellular sort of devices. Right, why is it that we have different sort of modulation schemes? How we get high speeds, high data rates, right, versus low data rates, and how we mitigate around the signal to noise ratio issues. Okay.
Perfect.
Exactly.
Yep.
Right. So this is all about getting insights, right? This is what knowledge is all about, right? I prefer that you actually learn this, right? In terms of from a knowledge, right, Chantal, from a knowledge acquisition point of view, right? Rather than just always cramming for an exam. Okay. Understanding it is actually as a general knowledge, right, is a good thing for you. Okay. And the next time you ask for 8K, think twice. Maybe think 3 times. Right, so I'm going to end it here because I'm over the time, right? You guys can start logging off unless you have other questions. I'll stay online for a few minutes, right? But thank you very much. Then I'll see you guys again next week.
Thank you.
Thank you.
Yep,
See you next week.
Yep, bye-bye.
See you next week. Thank you.
Yep, see you. Thank you. This slide, right, Youngju? Okay. So are you there, Youngju? Yeah, okay. So remember, right, the amplitude required to transmit these symbols, right, for each symbol is actually the distance from the origin to each of these symbols. Do you agree that the distance, if I add them all up, this distance here, this distance here, this distance here, and this distance here, right? This distance, right? Oops, if I just break this. Can you see this? Do you see that the distances on B, if you add them all up, is longer than the distances in A? And therefore less power. And because we're transmitting B with more power, they're more separated. Oh, because power, right, is voltage times I. Power equals to V times I. I'm saying not the precise calculation of power in watts, but voltage, right? No, but not that we need more I, because we have more. We need more V. The red lines indicate the voltages, which is the amplitudes. Assuming equal current, right? The more voltage required, right, the more power is required as well. Does that make sense? Because the more voltage equates to more power required. So B requires more voltage than A, which means more power than A. But the benefit of it is that if you have more voltage in more power, you get better separation and therefore more resiliency to errors. Is that clear? Yeah, no problem. Okay, again, you have time to ask me a question next week. Okay, thank you guys.